Okay, welcome back to our graphs of rational functions, moments with Meyer. Here we go. We are going to, okay, now this bottom part, in all seriousness here, this bottom part, the directions are going to sound kind of crazy. But I'm going to do my best to try to put them into terms in which you can understand. So we are going to describe how the graph of the given rational function, okay, so this given rational function is 4x plus 10 divided by x plus 3, how it can be obtained by transforming the graph of the reciprocal function, which is actually the parent function of 4x plus 10 divided by x plus 3. It's going to be a methodical step that we're going to go through. Sorry, power outage. Just kidding. It's a methodical process. And so it's a 1, 2, 3, 4, 5 steps that we're going to go through. I'm going to write out the 5 steps verbally, and then we're going to work it through algebraically. We're going to end up by using the transformations that we talked about. I'm guessing it was like back in 1/6-ish or something like that, where we shifted, we stretched, we flipped, and so we're going to actually get to where we're going to see this function, how it can be transformed from the parent function, the reciprocal function 1 over x. Okay, so like I said, it's very methodical as we go through, and I want you to, on your notes, because we're going to do a separate problem over here, so I don't want you to get so excited as you're writing through the original function, take up all that space. So I need a little bit of space over here because we're going to have an extra example that we're going to do over here when we're finished, okay? So the first step, and like I said, we're going to write it out over here verbally, and then we're going to perform that step algebraically. So the first step, we want to rewrite, if needed, numerator in standard form. Okay, so we need to make sure that the numerator is in standard form. Then I'm going to come up here, work number 1. So I ask you, is 4x plus 10 in standard form already? Yes. The answer is yes. S standards, that is short for standard. Rewrite numerator, and you're going to see that I do a lot of shortcuts with my writing, so rewrite numerator in standard form, okay? And I'm not going to abbreviate, tell you what those initials are, because now I realize what I did, but that's okay. Standard form, all right? 4x plus 10. Second step, we're going to divide by denominator to find a remainder. And we're going to use synthetic division for that. And the purpose of rewriting it in standard form is so that we are already set up in order to do our synthetic division, because we need it to be, the numerator to be in standard form before we can do synthetic division. All right, so step number 2, we're going to set up our synthetic division. Because before I move on, I want you to look at our original function, 4x plus 10 divided by x plus 3. That fraction symbol, I don't care if you're back to when you were first learning how to do fractions, 1/2 is the same thing as saying 1 divided by 2. That fraction symbol means division. So if we get a little confused on this, we're doing nothing more than just what this function is telling us to do already. Okay, making sure first of all that that numerator is standard form, and now we're going to be dividing. Now, this looks like we've got x plus 3, and if I was asking you, is x plus 3 a factor of this function, what would I divide by? What would be my value in which I would pull out of here to use for my division? -3. Same principle. I'm not changing anything on you. Same principle. So I'm going to be pulling out a -3. Now understand, I'm not saying that this is a 0. And as what we've seen in previous lessons, if it's a 0, what would my remainder be? 0. So if you end up with not a 0 for the remainder, don't be startled. don't think you've done anything wrong, more often than not, you will end up with not. This will not be a 0 of that, or a factor of that function, okay? So I'm going to take this and divide by -3. So now we just perform our synthetic division. We bring down our 4, multiply, add, multiply, add, multiply, add is our synthetic division. That becomes -12. Subtract that, I end up with a remainder of -2. I do like to box out this -2, and in this situation makes it you can see why it is so important to have that little box around the -2, because this problem that we did for synthetic is probably one of the simpler ones we've ever done. It's only been like just one step that we did here. One multiply, one add. Typically, we've got a degree of 5 that we're, using our synthetic division on, so we have several different coefficients that we have as our answers down below, but here we only have 1. And so if you know that this is your remainder, the coefficient to the left is your constant. This is your constant. Out, if coefficient out in front of the constant would be degree 1, degree 2, degree 3, on and on. But because, very rarely do we see one with just a constant. So the third step is we're going to utilize our answer. So third step is we're going to rewrite it rewrite our solution. Okay, so this is 4 minus 2, and if that's the remainder, remember we put the remainder over our divisor. So 4 minus 2 over x plus 3. Now I ask you, 4 minus 2 over x plus 3, is that the same thing as saying -2 over x plus 3 plus 4? Can I call those equivalent? Absolutely. All I did is just move the 4 to the other side. And the purpose of doing that is what we're going to be seeing in step number 4. So far, what we've done here is pretty much some stuff, everything that we've seen before. Nothing new. Step 4 is where we're going to see a little bit, we're going to get a little bit trickier. We are going to rewrite again, but this time we're going to rewrite using function notation. We're going to utilize substitution. Now remember, f of x, if we go back to our function, and if you guys can all, you finish writing, but I want your eyes up front, because this is where it gets a little tricky and kind of hard to understand a little bit. The reciprocal function is written in function notation, f of x equals 1 over x. Okay, 1 over x is the reciprocal function. Kind of get that function in your head of what that looks like. Kind of did the little break off deal. So that's 1 over x. The reason why it's 1 over x is because f of x means that x is being plugged in right down in the denominator. Wherever x is, I'm putting in an x. So f of x is the same thing as 1 over x. So if I should change my input, my x value, then that, whatever I put inside these parentheses, will go in that denominator. Everybody with me? Okay, now I'm going to kind of squirrel on you a little bit. And I want to ask you this question. If I have -2 over x plus 3, is that the same thing as saying -2 times 1 over x plus 3? Do I have equivalent values there? Okay, everybody take a second and really study that, because that is the key to what we're about ready to do. So now what I'm going to say here is that x of my f of x is going to become x plus 3. So in essence, what I'm going to be doing is I'm going to say f of x plus 3 will be 1 over x plus 3. You with me? So if I put a y here, this would be 1 over y. If I put a 2 here, it would be 1 over 2. If I put a 12 here, it would be 1 over 12. If I put a f of x squared plus 2x plus 3, I would have 1 over x squared plus 2x plus 3. That's all we're doing. We're just substituting in a new value for x. Okay? Everybody got that? Okay. So what I'm going to do now is I'm going to, looking at this right here, I'm going to pull out my -2. And I know this is going to look kind of funky, f for funky. I'm going to put in the function notation, f. But instead of saying f of x, guess what I'm going to put here? F of x plus 3. Then my plus 4. So what I have is right here, what I have circled up above. I have -2 times 1 over x plus 3. It's written a little different, but it means the exact same thing because of what's given above, plus 4. What I have now written, and that's a negative, what I have now written is in a form in which now I can pull out my transformations. That was my goal. So starting from the left-hand side, what does the negative in front of this function represent? Remember that? Reflection over the x-axis. Okay, we're going to have to reflect over the x-axis. What's the 2 out in front of the function represent?
Vertical stretch.
Vertical stretch by a factor of 2. I'm running out of room, so I'm kind of abbreviating that a little bit. Vertical stretch by a factor of 2. Then I go into.
She made a mistake, so she corrected it.
Oh, thank you.
Translated left 3.
Okay. So then I shift left 3.
And up 4.
And then I move vertical up 4.
What do we write for a 5 step over on the other side?
Say who what?
Like in words, what do we write for a 5?
I'm going to give you a brand new function. We're going to work a brand new problem.
Okay.
Okay? So let's just kind of refresh on this. First thing, numerator, standard form. Purpose of that is so that we can move straight into synthetic division. Using synthetic division, I could write it out saying dividing the numerator by the denominator. Okay? Pulling out that -3. And then once I have that, I write that into my solution. So it's just 4 minus 2 over x plus 3, which is, you know, now I have a factor of that. So if I take x plus 3 times this, I get back to my original problem. So I have 4 minus x plus 3. I just rewrote that, moving the 4 over to the other side so that I could get it, so that I could write it into function notation to pull out my transformations. And this is the same thing as saying -2 times 1 over x plus 3. I don't need to show the 1 over because that is represented with my f, meaning what was my original function I was using? My reciprocal function, which is 1 over x plus, or excuse me, just 1 over x. But instead of plugging in x for that, I'm plugging in x plus 3. So it means the exact same thing. So that's -2 times 1 over x plus 3 plus 4. Then rewrote out my transformations. Okay? New problem. F of x equals, actually I should say g of x because f of x is still 1 over x. So g of x equals 4 minus 3x over x minus 5. So g of x, even though that looks like a really squirrely g of x equals 4 minus 3x divided by x minus 5. Step 1. And just follow, I'm not going to rewrite it out, but just follow along with what we have verbally written out over on the left-hand side. Standard form becomes -3x plus 4. Because if you would do synthetic division on 4 and then -3, wrong answer. So number 2, I set up my synthetic division, dividing by a +5. And again, do not be afraid of those, higher remainders. We're used to remainders of 0 from our previous lessons because they were zeros of the function. This is not necessarily the case. Then I rewrite it as -3 minus 11 over x minus 5. I'm just going to say, move the -3 over to the other side just to make it easier when I go to write it in function notation. And then, so far, nothing's new. All of step 1, 2, 3 should be a breeze at this point in the game. Number 4, I'll give you a little bit of credit if we kind of have to stop and scratch our head a little bit on that one. So this is the same thing as saying -11 times 1 over x minus 5. So I write that as -11. I got to put that f in there to represent I'm substituting in for that function. X minus 5 minus 3.
Would it be G?
G. No, because I'm substituting in for the original function f.
Oh.
But good question, good question. Then I can write out my transformations. That's my goal.
So you always use the original function?
Yes, because I'm substituting in for this right here, because that's what I'm comparing it to. I'm making a comparison to the original parent function of the reciprocal function. What movement, what transformations took place to get from my g of x from the original parent function f of x. In order to figure out those transformations without having to go through all the graphing, I can do it algebraically. So again, I have a reflect over the x. I have a vertical stretch. Factor of 11. I'm moving right 5, and I'm going down 3. Right 5, down 3 is shorthand, but just know I'm shifting right by a factor of 5, vertically shifting down by a factor of 3. Okay? Questions on that? Okay, real quick. Well, I'm going to come back, remind me to come back and make the changes to this homework assignment, okay, because I've got a few changes on that. Okay, flip to the other side. And for those of you that have been with me from the beginning, you will understand what we're talking about here. For those of you that have not, you're going to find a really cool shortcut, or it's not a shortcut, but just an acronym on ways to remember horizontal asymptotes just a little bit easier. And at the top of this page, this whole entire page, we're talking about asymptotes. Or you could say asymptote, okay? That's how it's spelled, asymptote. So these are asymptotes that we're talking about here. The first two, we're really looking at horizontal. And then at the bottom, we're going to get into a new one that we have not yet talked about called a slant asymptote, okay? So we've heard vertical, we've heard horizontal, and now we're going to be looking at slant asymptotes. So number 1 and 2, I'm not going to go into great detail on because we've already covered that. But if the denominator is greater than the numerator, the end behavior is 0. In this class, we know that as BOBO, big on bottom, horizontal asymptote at 0. That's our acronym for number 1. We've been there, we've done that. Number 2, if the denominator equals the numerator degree, if the denominator degree equals the numerator degree, we know that as EATS DC. Exponents are the same, aka the degree, if you want to be mathematically correct about that, it's the largest exponent, the degree. The degrees are the same, then you divide coefficients. And that's exactly what's written out here. Then we get to number 3, where it says if the numerator is greater than the denominator, there is no horizontal asymptote. That's my bottom. Big on top, no horizontal asymptote. So what happens if there is no horizontal asymptote? There is a case that there could be what's called a slant asymptote, and that's what we're going to be talking about down below. And like I said, I'm not going to go into all of this because we basically, when we were originally talking about horizontal asymptotes, we've already covered that, okay? So our new information is down here, and we're going to find what's called a slant asymptote, okay? So first thing you need to understand is that what we did with the transformations, how we had to have the numerator in standard form, and then we used synthetic division, and then we rewrote the answer. That's exactly, those first 3 steps are exactly what we're going to be doing on the slant asymptote as well. Okay? Nothing is going to change on that. We're not rewriting it in function notation like what we did with the transformations, but on here, we're just going to do those first 3. So the first step is this in standard form? Is that in standard form? I would say yes. So then I'm going to go straight into synthetic division. And what we're doing by doing this synthetic division is we're locating and finding a slant asymptote. We're looking for the equation. Let me rephrase that. We're looking for the equation of the slant asymptote, because the horizontal asymptote has an equation of y equals 0 if it's 0, or y equals 1, whatever the wherever the horizontal asymptote may be located. A vertical asymptote would be x equals 0 if it's on the y-axis, or x equals 2 if it's a vertical asymptote of 2 at 2. And so we have equations for horizontal and vertical, but how do we find the equation of a slant if a slant does exist? So this is the method in which to find that equation. So I've got my numerator in standard form, and now I'm going to divide, because that's what the fraction bar means. And if I've got x plus 2, what am I going to divide by? -2. You got it. Bring down my 1. Remember, it's mama. Multiply, add, multiply, add, multiply, add. -2 times 1, -2. Box out my remainder. So I should have a remainder of 13. Again, do not be afraid of those remainders that we may see. Okay, so now the second step is I'm going to write the equation. Actually, the first step, if I wanted to be correct, make sure it's in standard form. And then synthetic, and then write the equation. Now remember, this is my remainder. -5 would represent my constant. X would represent my degree 1. Okay, my degree 1, because it's always 1 less than in synthetic. To write the answer, it's always 1 less the degree that's written. So this becomes x minus 5, oops, sorry, didn't mean to put that there, plus 13 over x plus 2. Actually, I'm going to incorporate that and pretend like I didn't make a mistake. Okay? So I've got x minus 5 plus 13 over x plus 2. X minus 5 is my slant asymptote. X minus 5, ignoring the remainder, that's nominal. Ignoring the remainder, I have my x minus 5 written out there as a linear equation. So in essence, x minus 5 is a line, y equals mx plus b, because remember again, a horizontal asymptote had a linear equation, vertical asymptote, same thing. So a slant asymptote doesn't want to be left out of the party. It too is going to have a linear equation. And I'm going to see slope is 1. My y-intercept is -5. So a slant asymptote, we graph it. So if I would say, find the slant asymptote and graph given this equation, you would do all of this, synthetic, rewrite it, and then utilizing slope and y-intercept, you'd be able to graph that slant asymptote. Okay, so what I want you to do now is grab your calculator, because I want you to visually see this, and I want you to put in f of x, the original function. So we're going to type in x squared and make sure that in front, bless you, you include your parentheses appropriately, unlike the teacher right now. Okay, so x squared minus 3x plus 3 divided by parenthesis x plus 2. And if you look at the original function, my degree is bigger on top, so it would fit. If I was just looking for horizontal asymptotes, it would fit the bottom, big on top, no horizontal asymptote. So I wouldn't, I'd say there is no horizontal asymptote. And in that case, if there's no horizontal asymptote, when I go to write my end behavior, the behavior takes on the behavior of whatever the graph is. And if you go back to the notes, that's basically what is being talked about right here. That we've already, I don't want to be redundant, we've already talked about that. So if we look at this graph here, can you see where, this is sometimes how I feel Monday mornings, where you're a little off, a little off kilter a little bit. It's not a perfect parabola by any means, so you're just a little off. This poor little guy's just a little off. But you can see where this right-hand side could form a slant. This is where I would have a slant asymptote. So if you look at that, if you go down to -5 on the y-axis, and then if you up 1 over 1, up 1 over 1 for your slope, you can see where that would form a nice a nice slant asymptote right there with that graph, okay? Now it says I also want to find the end behavior of this graph as x approaches -infinity. So if I go from the origin, move into the left, what is the function doing? What's the behavior of the function as x is going to the left? If I had an arrow, it would be pointing up or down on the end of this graph. Up, so it would be positive infinity. Going to the right, as x approaches positive infinity, as x goes to the right, what's the graph doing? Also going up, so positive infinity. So if I want to write this as limit notation for end behavior, so the limit of the function as x approaches -infinity would be positive infinity. The limit of the function as x approaches positive infinity is still positive infinity. So both parts of that graph are headed up into positive infinity. Okay? So that concludes our time with Moments for Meyer on day 2 of 2.6.